Helium is the second most abundant element in the universe. It powers the sun. It fills party balloons. And it is one of the most strategically critical materials on Earth. Unlike almost every other resource, helium cannot be commercially synthesized. It's produced underground by the alpha decay of uranium-238 and thorium-232 over billions of years. It seeps into natural gas deposits. The only way to get it is to extract it as a byproduct of natural gas processing. When a gas field is tapped, the helium comes with it. When the field is shut down, the helium supply stops. There is no alternative source at industrial scale. And once helium escapes into the open atmosphere, it's so light that it rises past Earth's gravitational hold and is lost to space forever. The world's largest natural gas field sits under the Persian Gulf, straddling the border between Qatar and Iran. Qatar calls its portion the North Field. Iran calls its side South Pars. Together, they contain roughly 40 to 50% of the world's known helium reserves. As of 2025, Qatar is the world's largest helium producer. It surpassed the United States after the privatization of the U.S. Federal Helium Reserve and the massive North Field expansion projects came online. The helium is extracted at Ras Laffan Industrial City, the same facility that processes Qatar's liquefied natural gas for export through the Strait of Hormuz. When the strait was disrupted in March 2026, it didn't just stop LNG shipments. It stopped helium shipments. The gas that cools your MRI, that enables your chip manufacturing, that runs particle accelerators, its supply chain runs through the same 21-mile choke point as your gasoline. An MRI machine works by creating a magnetic field strong enough to align the hydrogen atoms in your body. The magnet that creates this field is a superconducting coil, typically niobium titanium wire that carries electrical current with zero resistance. But superconductivity only works at extreme cold. The coil must be cooled to 4.2 Kelvin, that's minus 269 degrees Celsius, just 4 degrees above absolute zero. The standard coolant is liquid helium. Newer MRI designs are changing this. Philips has developed a sealed magnet system that uses just 7 liters of helium instead of the traditional 1,500 and never needs refilling. But the majority of the world's installed MRI fleet, especially the high-field 3 Tesla machines used for detailed brain and cardiac imaging, still depends on large helium reservoirs. Older systems experience helium boil-off and need regular refilling. Modern zero boil-off systems recapture and reliquefy the gas internally, but even these need helium during installation and after emergency quench events. When helium supply is disrupted, hospitals don't lose MRI capability overnight, they lose it gradually, machine by machine. Semiconductor manufacturing is one of the most precise industrial processes ever created. Modern chips have features measured in nanometers. Creating those features requires extreme ultraviolet lithography EUV machines that project patterns onto silicon wafers using light with a wavelength of just 13.5 nanometers. These machines, built exclusively by ASML, cost roughly $380 million each for the latest high-NA models. And they depend on helium. Helium is used as a purge gas inside the lithography chamber because it's chemically inert. It's used to cool the tin plasma that generates the EUV light. And it's used in leak detection across the vacuum systems. Helium's tiny atomic size makes it the gold standard for finding microscopic leaks. A semiconductor fab uses between 500 and 2,000 liquid liters of helium per day depending on production volume. Modern fabs use closed-loop recovery systems that recapture over 95% of the helium. But even with recovery, the base supply must be reliable. When helium prices spike or supply becomes uncertain, fabs slow down. Yields drop. Production schedules slip. The cost of every chip in your phone, your car, your laptop rises. This isn't the first helium supply crisis. The industry has experienced 3 formally recognized shortages in 2006, 2012, and a prolonged crisis from 2019 to 2022 known as Shortage 4.0. Each time, MRI machines went offline, research labs rationed supply, and semiconductor fabs paid emergency premiums. The 2026 disruption represents a new market tightening driven by geopolitics rather than infrastructure failures. The U.S. Federal Helium Reserve, stored underground in the Bush Dome Reservoir near Amarillo, Texas since 1925, was once the world's strategic buffer. But Congress mandated its sell-off with the Helium Privatization Act of 1996, and the reserve was fully transferred to private ownership in 2024. There is no longer a government-mandated strategic helium stockpile anywhere in the world. When supply is disrupted, the disruption passes directly to users. Here's the paradox. Helium is roughly 24% of all matter in the universe by mass. The Sun converts about 600 million tons of hydrogen into helium every second through proton-proton chain fusion. The universe is overflowing with it. But on Earth, helium is functionally non-renewable. The helium trapped underground took billions of years to accumulate. We are extracting it in decades. And unlike oil, which can be replaced by solar and batteries, helium has no substitute for its most critical applications. You cannot purge an EUV chamber with anything else. You cannot run certain particle physics experiments without it. And while new MRI designs are reducing helium dependency, the global installed base of 70,000 plus MRI machines still overwhelmingly depends on it. The universe's second most common element is becoming one of Earth's rarest strategic resources. The immediate crisis will pass. But the structural vulnerability remains. Research into helium recycling closed-loop recovery that recaptures 95% or more is already standard in advanced semiconductor fabs. Sealed MRI magnets using just 7 liters are entering the market. ASML and chip manufacturers are investing in recovery infrastructure. But replacing the global installed base of helium-dependent equipment takes years, not months. In the meantime, every hospital, every chip fab, and every research lab depends on a supply chain that starts under the Persian Gulf, now the world's largest source, and passes through a 21-mile-wide strait. Helium. Too light to stay on Earth. Too critical to live without. Too concentrated in one place to be safe. The machines that scan our bodies and manufacture our future depend on a gas formed by radioactive decay billions of years ago, trapped by geological accident, and shipped through the narrowest waterway in global trade.